Okay, quick review from last class. We had started the chain rule. We had looked at a pattern and started to notice that it seemed like you could do your exponent or power rule. Bring the power out in front, subtract 1 from the exponent. But there was always something extra which we underlined in blue. And then we realized that the extra that's underlined in blue is just the derivative of the inside. And so we wrote out, or we looked at what's on the formula sheet. And if I color code things the same way, we have derivative of our inside function, derivative of our outside function, and then we multiply by the derivative of our inside function. In the examples that we looked at, we just had the power rule. But you could have different functions inside of different functions. You could have a cosine function inside of a sine function. Then you could use a chain rule. You could have a, let's say, a power inside of e to the x. Then you'd have the chain rule. And in fact, we'll even look at what happens when you have, what would happen if you had sine inside of cos, and then that was inside of tan? Well, then you would have an inside function inside of another inside function inside of another function. And we could use the chain rule. So this is the idea. Now we're going to look at some examples of how this works. The power rules are the most straightforward. Now, for this example, I'm going to look at how you could use the formula. So if we're using this formula here, what you need to do is label your inside function. So in this case, my inside function is 3x plus 6. I'm going to make that u. The derivative of my inside function is 3. And then my equation could be rewritten instead of y equals 3x plus 6 to the 5. I could write y equals u to the 5. And then the derivative here, dy du, is 5u to the 4. Now, I'm using the formula here for the most part. Since you've already seen the pattern and can think about doing the derivative of the outside function and then the derivative of the inside function, you will be able to do it directly and quick. And it will be easy. But for now, we're going to think about the formula. Okay? Maybe you're sensing a little bit of bias from me right now. That is dy du, and that's a y. So then, if y is u to the 5, then dy dx would equal, okay? I'll write out the formula. Dy dx is dy du du dx. So dy du is 5u to the 4. Du dx is 3. And then afterwards, we can substitute things back in and simplify a little bit. 5 times 3 is 15. Okay? What do I want you to do, though? I want you to go directly from here. I think you can go, there we go, to there. Can you see yourself doing directly from there to there, saying, hey, I could bring the 5 out in front, keep the inside the same, subtract 1 from the exponent, and then multiply by the derivative of the inside function? Can you see yourself going directly from there to there? I hope so.
Teachers just letting you know the grade 10 girls group of 16 was running late. They're being.
Okay. So if you go directly from there to there, things are good. Because if you use the formula every time, especially when we get into more complicated one, it sucks. I don't like the formula. So instead, what we're going to think about is, can we recognize what's the function inside, what's the function outside? Do the derivative of the outside function with keeping the inside one the same, and then do the derivative of the inside function. Oops. Okay. So, looking at our second one. Find dy dx. First of all, I recognize that 5x cubed plus 2 is inside something to the power of 6. So when I want to do my derivative, dy dx, I want to do the outside function first, which is the power of 6. If you had a power of 6, what would you do with it? Bring the 6 out in front. Can you see that would give you a 24? Then you would subtract 1 from the exponent. Keep the inside function the same. And then multiply by 15x squared. And just like our product rule and our quotient rule, most of the time you don't even have to simplify. Because you can see you could multiply the 24 times the 15, right, if you wanted to. But for the most part, they're fine if you just leave your answer like this. Again, can do it in one step. No need to take out your formula, rewrite everything, substitute things in, substitute things again. We want to be able to do these directly. So we want to find the gradient function. That's the same thing as the derivative for this equation. I see that I have an x squared plus x inside of a power of 4, but that power of 4 is in my denominator. So sometimes, even though we have lots of rules already, okay, and you are allowed to use any combination of rules that you like, sometimes it does make sense to do a little bit of manipulation beforehand. So in this example, what I'm going to do before I start is change that power to the 4 that's in my denominator to a power of -4 in my numerator. Because now I can do my power rule. Can you see in the original question you can't do the power rule because it's on the bottom. You could do a quotient rule. Okay? So I'm going to put a line here and do the little bit not as desirable quotient rule second. So if you decided to use the quotient rule first, I'll show you how that works. I'm going to show you why changing it this way will make it easier.
When you bring up that part,
Yep.
like you don't have to flip the 3 to the bottom, right?
No.
You just like
Because the 3 is in the numerator already.
the exponent.
Yeah.
You don't have to like flip it.
No. You're not doing a reciprocal here. You're just taking the exponent part and moving that from the denominator to the numerator. So with that in mind, now we could use, whoa, I didn't want to change to black. Right? My outside function is the power. How do I do a derivative of power? The -4 would come out in front, keep the inside the same, subtract 1 from the exponent. Then the derivative of my inside function, 2x plus 1. There's a nice final answer. If you had said, oh, I thought of the quotient rule. It works as well. Okay? Anybody take their 2 minutes on Monday at lunch to memorize the quotient rule? No. Okay. So, again, all of these rules, you will use them so much that if you take a little bit of time early to memorize them, you will more than save that amount later on. Because every time you have to flip to find something, it's going to take you time. So I strongly suggest take the time now with all of your derivatives and all of your derivative rules to memorize them now. And if you ever are unsure, okay, nice thing, because sometimes that happens with something you've memorized, right? Ever been in a test or an exam where you go, oh, I think that's what it is, but I'm not sure, right? Well, then you still have your formula book. You could check it and go, oh, yeah, I was right. Or, ooh, yeah, I was wrong, but I'm glad I checked it. But we want to mostly memorize it, especially while you're doing your homework, because in your homework, you're checking your answer. And if your answer matches up, it's obvious that you memorized it correctly. Okay, so using the quotient rule. The quotient rule says keep the bottom the same. X squared plus x to the 4. Multiply by the derivative of the top. What's the derivative of 3? 0. Subtract. Keep the top the same. 3. Multiply by the derivative of the bottom. Well, the derivative of the bottom is a chain rule. So you would have 4 come out in front. Keep the inside the same. Subtract 1 from the exponent. Multiply by, wow. Slowly move things over. Multiply by the derivative of the inside. All over the bottom squared. Squaring the 4th will make it to the 8. The question is, can you see that these two answers are the same? Just the one on the right looks messier. First of all, the one on the right, can you see this times by 0? This is going to be 0. Okay. Can you see that I have negative 3 times 4? I'm going to get negative 12. This one I have x squared plus x to the negative 5. This one I have x squared plus x to the 3 on the top and x squared plus x to the 8 on the bottom. If I simplified that, I would get x squared plus x to the 5 on the bottom, which is same as x squared plus x to the negative 5. And then you still have the multiply by 2x plus 1. So if you said, well, what happens if I chose the wrong derivative rule to do first? You can't choose the wrong derivative rule to do first. You can just choose one that's more work, or choose one that doesn't have as nice of a looking solution. But it's not wrong. So that's a nice thing to know. Okay? Can you see that you're using your power rule is probably easier than using your quotient rule? Okay? How many people have the power rule already memorized? That one feels like you've known that one forever, right? Quotient rule memorized? Okay, yeah, maybe, see? So obviously method 1 is better in that sense because it's something that's more familiar. Example 4. Again, we have to do a little bit of work initially. Right now, that's not in a form that I can do because I have that 5th root. But I can change a 5th root to an exponent of 1/5. And with that exponent of 1/5, now we can see the 3x squared plus 7x inside of a power. So how do we do the derivative with the chain rule? Outside function first. That 1/5 would come out in front. Inside stays the same. Subtract 1. Again, I said you were going to get really good at subtracting 1. And then derivative of the inside. Nice. All good? So now let's start to, here's the, change that radical to rational exponent hint. Now we can start to change things that don't just have polynomials and powers. Okay? Y equals sine squared x. First of all, do you know that when it's written that way, that it means the same thing as this? That mathematicians have just made that 2 go inside to be somewhat of a shortcut so they didn't have to write extra brackets. Right? Because this is not allowed to say the whole thing squared. That squared refers just to the x. Oh. In this case, can you see that sine x is inside of the squared? In this case, the x squared is inside of sine. Both of them could be a derivative with the chain rule, but they would be really different because of which function's inside of which. Cool. I'll do that one afterwards just for fun. Right? Fun. Okay. So, if you think of it this way, it's really easy to see that the sine x is inside of what's being squared. Can you see your brain confusing you here and saying, oh, the squared looks like it's inside of sine? It's kind of written inside, so it can cause you some problems that way. So initially, you might want to change it to this, just to help you see it. Because now, when I do the derivative, my outside function is the squared. That would come out in front. Subtract 1 from the exponent. You wouldn't need to write that 1, but you could. Multiplied by the derivative of the inside function. What's the derivative of sine? Positive cos. Okay? If this was a multiple choice question and the multiple choice question had this as the answer, would you have got it? What did I do? I used an identity. Okay? So here you're thinking derivatives, and in the middle of it, an identity shows up. Some of them. So all of your double angle identities are, your sum and difference are not, and they will not be on your exam.
I'd like to see.
That's what I like to hear. Okay. Of course, this would be there we go. That would be your final answer. Most likely. You would leave it as that. Just showing you an identity because it showed up. Okay? Same question. Would you agree that sine squared x is the same as sine x times sine x? Right? So you could have also chosen to use a product rule. Okay. Product rule would say, keep one the same, multiply by the derivative of the other one, then add, keep the other one the same, but they're both the same, and multiply by the derivative of the other one. So you would get sine x cos x plus sine x cos x, which those are like terms, would give you 2 sine x cos x as your answer, same answer that we had on the other side. So again, depending on how you view the question, you have more than one method to look at this. Okay? Now let's do the fun one just for fun. If you had sine x squared. And this is where the language that I've been using all along is going to help you figure things out. So what do? We have to figure out what's the outside function, what's the inside function. In this case, the x squared is inside of sine of x. So we always do the derivative of your outside function first. So sine is our outside function. The derivative of sine is cos. Keep the inside the same. And then multiply by the derivative of the inside function, which would be 2x. So when we do the derivative of the outside function, and the most common mistake with the chain rule is that people over-derive. They want to do too much derivatives at once. You just do the derivative of the outside function. Derivative of sine is cos. Keep the inside the same. And then multiply by the derivative of the inside function. All right. Next level. What's the outside function? The squared. So you may want to, at this point, write it like that. Does that make sense? Yes. The outside function is the squared. What's inside? Cos 5x. But when we think about the inside, can you see that the 5x is inside of cos x? So we have a chain rule inside of a chain rule. The cos 5x is another chain rule because there's another function inside of something else. So we have to follow our words here. If I tried to do this with a formula, oh my goodness, I could make sure all of you fail. Like, it becomes the most complicated letter. We have to like introduce u's and w's and but if we just follow the logic of the words of the chain rule, we're going to be fine. What does the chain rule say? Do the derivative of the outside function. 2 comes out in front. Keep the inside the same. That's step 1. And then we multiply by the derivative of the inside function. Now, when we get to the derivative of the inside function, it's another chain rule. So we have to start our words again, right? So if I want to do the derivative of the inside function, which is another chain rule, I now have a new outside function and a new inside function. Cos is on the outside, 5x is on the inside. So the derivative of cos, negative sine, keep the inside the same, multiply by the derivative of the inside. Should we talk about that again? Follow it through again? So initially, my outside function was squared. That 2 comes out in front, subtract 1 from the exponent. I kept the inside the same. And then I have to multiply by the derivative of the inside. But when I think about my inside, it's another chain rule with a new outside of cos and a new inside of 5x. So the derivative of cos is negative sine. I kept my new inside the same, and then multiplied by the derivative of that inside, 5. So the most difficult thing with the chain rule is just deciphering what's inside of what in different situations. Can you see that the 2x squared is inside of e to the x? Okay? Just plain with notations. If I called h of x e to the x, and I called g of x 2x squared, does it make sense that g of x is inside of h of x? If I do composition of functions like this, well, what does this mean? This means h of 2x squared. And how do we do function notation? Whatever's inside replaces the x. That's just a review of function notations. So when I say 2x squared is inside of e to the x, this is the function notation that explains that. G to the x here is in h of x, inside of it. Then when we're doing our derivative, f prime of x, we have to do the derivative of our outside function first. Our outside function, that's e to the x. What's the derivative of e to the x? E to the x. So it's do the derivative, keep the inside function the same. So our derivative of the outside function just keeps everything the same. And then we have to multiply by the derivative of our inside function, which is 4x. And because e to the x doesn't change, it makes you all somewhat confused because you're like, I feel like I didn't really do anything. But you did. You did the derivative of e to the x, which kept everything the same, and then multiplied by the derivative of the inside function. So try this one. And how did you do? Kept e to the sine x the same, then the derivative of the inside function is just cos x. I want you to try number 9 on your own as well. And if you finish number 9, try that one. And then think about what's different between those two. I'm having too much fun. And what's different between this one? Oh my goodness. Yeah, I feel like I want to do them afterwards. Oh, I should put it on pause. Oh, you want to check these ones first? Did you do this as your first step? Change it to 1/2, move it up? Did anybody use the quotient rule? No. Good. You could simplify it if you wanted to, but I would leave it as that second line there. And then let's look at the purple, the green, and the black. Can you see how they all look similar? Okay. I wrote the green one first, so let's do the green one first. And let's look at the green and the purple. What rule is the green one? What rule would we use? It's going to be yes, it is the chain rule. Why? Can you see that the tan x is inside of natural log of x? The tan x is inside the natural log. What's the purple one? It's not a chain rule. It's a product rule. Okay? Now, can you see yourself accidentally thinking one is a product rule when it isn't? Like that green one, can you see yourself on an exam going, oh, ln times tan of x, and thinking it's a product rule, and then going and doing your product rule instead of a chain rule? So it's important to recognize these small differences. So for the green one, if I was doing the derivative, do you remember the derivative of natural log? 1 over x. So we do the derivative of our outside function is 1 over, keep the inside the same, so it'll be 1 over tan x multiplied. Anyone remember the derivative of tan x? Secant squared x. So that's the answer to the green one. The answer to the purple one. Do the derivative of one function, keep the second function the same, plus keep the first function the same, derivative of the second function. There's your product rule. And the third one. Can you see that the third one is a chain rule because something's inside of natural log, but it's also a product rule because the inside function is a product rule? Okay. So again, you have to know your rules and just walk yourself through it slowly. So I see x tan x inside of natural log. So I'm going to start with my chain rule and say, chain rule says, do the derivative of the outside function, which will be 1 over, keep the inside function the same. Multiply by the derivative of the inside function, and my inside function is a product rule. So how do I do a product rule? Do the derivative of one, keep the other the same, plus I'm going to talk it through differently. Keep one the same, derivative of the other one, keep the other one the same, derivative of the first. And so we had 3 equations that were very similar to begin with in how they looked, but the derivatives look quite different for all 3 of them. Work backwards. This was the derivative. Find a function y with this derivative. Did anybody have something different? Nobody wanted, like, because you could have had right? Maybe your favorite number. Add it on. Or whatever number there, right? But you wouldn't need to. This is fine. The last question is a typical exam question here. They give you two functions, f of x and g of x. And it says, can you write down the derivatives of each of them? Can you see that each of them have functions inside of other functions? So for f of x, the negative 3x is inside of e to the x. So we'd have a chain rule when we do the derivative. E to the negative 3x times by a negative 3, which you could write that negative 3 out in front. The second one has x minus pi over 3 inside of sine of x. If you did that as a chain rule, well, derivative of sine is cos. Keep the inside the same. What's the derivative of the inside? 1. So you could write times 1 if you wanted to, but you don't need to. For the derivative, you could write if you wanted to, right? I'll do it in a different color even. What's the derivative of the inside function? 1. So I could do times by 1. It's not wrong to write it there, but I didn't have to write it there because times it by 1 just keeps it the same. Now read part B. Let h of x equal e to the negative 3x sine of x minus pi over 3. Find the exact value of h prime of pi over 3. So does it feel in part B that they just took this question to a different level quickly? They introduced a new function, h of x, and they want you to find the value of h prime at a certain value. Two things that could happen here. One, you could work at this completely separate from A and B. But on IB exams, when they do, or completely separate from AI and AII. But on IB exams, when they start something new in the same question, often they like to connect it to what you've done before. Okay? First of all, can you see that h of x is just a product rule of what we had before? And so when you go to do the derivative, you've already got all of your answers, right? Keep one the same, derivative of the second one, which you could steal from here. Plus keep the second one the same, derivative of the first one, which you could just steal from there. Now, if we wanted to simplify this, we could notice that this e to the minus 3x is in both of these expressions, and you could factor that common factor out. Factoring out a common factor in complicated expressions comes up more and more often in calculus. The reason it's nice to factor this out is because now, if you plug in pi over 3, this just becomes e to the negative pi. And you get cos of 0 minus 3 sine of 0. And it goes back to your unit circle. What's cos of 0? What's sine of 0? Which one's the x-coordinate? Which one's the y-coordinate? That's right. The x-coordinate is 1, so cos of 0 will be 1. Y-coordinate is 0. And it just becomes e to the negative pi.